Hi, everybody. I'm recording this lecture as an addendum to Lecture 12 in Dynamics. The reason is I started working out problem 1385, which is about orbital mechanics. And about halfway through, I realized that I'd never really explained to you the concept of escape velocity, which, if you don't understand what escape velocity is, it's very difficult to understand what terms go to zero in this problem. So I wanted to do a short lecture to sort of correct that problem. So what escape velocity refers to is if you launch a rocket from the Earth, for example, and if you launch it at the proper speed, it will go into orbit at whatever altitude above the Earth you desire it to go into orbit. Because the potential energy and the kinetic energy of the rocket on Earth are all the energy that that rocket is going to have when it is in orbit. So if the potential and kinetic energy exceeds what it needs to go into orbit, that is referred to as escape velocity. That is the velocity that's required on Earth in order for an object to not become part of Earth's gravitational field. In other words, to have too high of an energy and to therefore be able to escape orbit. Now, what happens if you think about it as escape orbit? You have a body that flies into the atmosphere, and then instead of being pulled back into orbit, it just flies off. So from a point of view of the orbit, the potential and kinetic energy of that trajectory are actually zero, because they are not subjected to the Earth's gravity, and that object will actually go off into space without being influenced by the Earth at all. So what that means is that the final velocity is going to be equal to zero, because according to this equation, the final potential energy is going to be equal to zero, because r, or its orbital distance above the Earth, goes to infinity. So this term divided by infinity approaches zero. Also at escape, this should be the velocity. This is the initial kinetic energy. This is the initial potential energy. The final kinetic energy is equal to zero because it's not in orbit, and the final potential energy is equal to zero. So what that means is that in the way that we find the value for escape velocity is to set the sum of t1 plus v1 equal to t2 plus t2 plus v2, which are both zero, or is equal to zero. So that's what this statement just basically says, is that t1 plus v1 equals zero. Now I've made the note that this is only used to determine escape parameters. This is not generally true, is it? In general, t1 plus v1 is equal to any t2 plus v2. But in this particular case, where escape velocity has been reached, this will give us the lower limit, or the velocity required in order to escape the Earth's velocity, or the Earth's gravitational field. So that means that 1/2 mv squared initially, when you're, in other words, the velocity that you launch the rocket with, minus gmm over r is going to equal zero, or that 1/2 mv escape squared is equal to gmm over r. All right, so if we go back to problem 13.5, it asks us, what is the kinetic energy per unit mass? So we start with this idea of the conservation of mass, and we're looking for the kinetic energy required in order to escape Earth velocity. So we know that T1 is equal to 1/2 mv squared. We know that V1, or the potential energy on Earth, is negative gmm over r. So what we're really looking for here is T1 over m. Okay, so if we go to that and we just say that's kinetic energy per unit mass, then it's going to equal that initial potential energy per unit mass, which is equal to capital Gm over r. So going back then to on Earth, that the weight is equal to mg and is also equal to gmm over r squared, we can look at this term and reduce it or solve it for gr squared being equal to gm. Now the reason we do that is because we want to do this substitution, which is instead of putting gm here, we want to put little gr squared. So then when we put little gr squared here and it divides by r, we're just left with little g times r. So in other words, in this very specific situation, the kinetic energy per unit mass required to reach escape velocity is equal to little g times r, or the radius of the Earth. So I plug those two numbers in, 9.81 meters per second squared times the radius of the Earth, which is 6.37 times 10 to the 6 meters, I get a value of 62.5 times 10 to the 6 meters squared per second squared. And then I just want to double check my units, because meters squared per second squared is not a good unit for energy per unit mass. If energy is in joules, kilojoules, or megajoules, then energy per unit mass would be, I have that 10 to the 6 here, so I suspect it's going to be megajoules. So I want to write this in megajoules, 10 to the 6th joules per kilogram. A joule is a Newton meter per kilogram. So if I plug in instead of that value, if I plug in kilograms here, and I have kilograms on the bottom, meter second times meter, I get that 10 to the 6th meters squared per second squared is equivalent to a megajoule per kilogram. So 62.5 times 10 to the 6th meters squared per second squared is the same amount as 62.5 megajoules per kilogram. And that's the answer to part A of 13.85. Now on the original vodcast on 12, on dynamics lecture number 12, I kind of went down a rabbit hole with this because I got halfway through the problem and I realized I really hadn't presented the material to make essentially this substitution, because I hadn't really talked about what escape velocity meant. I just went, well, you know, everything's zero at the top, and I didn't go into that discussion. So I wanted you to have this information so that the problem would make more sense. All right, so then this is just the working of the problem. These are the notes that I actually did in class. So I've posted these as well so you can see where that is. And I think I got a little trippy with my capital R and little r, but you have to remember on the Earth, r is the radius of the Earth. In orbit, r is equal to the radius of the Earth plus the altitude of the orbit. So when you do the conservation of energy, r goes to infinity, and then I just said, okay, well then it's equal to gm, which is what I just explained in this video. And at that point, we are able to arrive at this same identity, but T2 over m, once again, is equal to 0. So we can find that kinetic energy per unit mass. And after we find that, which is this value, we can then set that equal to that the kinetic energy per unit mass is equal to 1/2 v squared when we divide out the m, and then we come out with this value. So the velocity, the escape velocity then is 11.2 kilometers per second, which follows directly from the discussion above of escape velocity, or the energy at the top of that arc being equal to 0 in order for it to escape, and also the idea of kinetic energy per unit mass. All right, everybody, so I hope that clears things up. We'll see you in class today.